All right, this next lecture will be about how to deal with errors in our programs. Recall that there are many ways, as you know, there are many ways to make mistakes when you're programming. And in our language, the J7 language, here are a few example kinds of errors. So we could write 1 divided by 0. And this is an error because delta is partial on this particular function call. So recall that delta is the thing that defines our primitives, and it's not defined on divide 1 by 0. Here's another error. If we try to call a number as if it were a function. So function applications, they need either a lambda or a primitive. Other examples are things like we could do a set box, and we could give it, say, a number, and then the set box rule requires a pointer. Needs a box / pointer value. Okay, so those are all different kinds of errors. Now the question is, what happens in our language when we try to run one of these things? Well, the thing is that our big step interpreter is defined to be something like this, where when we want to evaluate a program, we're going to say that it's equal to a value if and only if that program, when we repeatedly call the small step interpreter, eventually gets that value. That means that this function eval is partial because this may never happen. And it may not happen for two reasons. It might not happen because the program might run forever, and it also might not happen because a program may go from program X to program Y to program Z, and then eventually it becomes 1 divided by 0, and at that point it just stops. There's no next step. It doesn't do anything. And so since it doesn't do anything, we say that the program is stuck. Stuck. All these things right here are examples of stuck programs, where our rules that define what a program means simply do not apply. So, what can we do? Well, the way that we typically represent this, you could also ask the question like, what does your CEK machine do? Your CEK machine doesn't get stuck. It probably just does something. And probably what it does is it maybe will crash or do undefined behavior if you've written it in C. For example, like the way that my thing works is when I try to do this 5, 1, it's just going to get an error because it's going to try to look at 5 and think that it is either a lambda, i.e. a closure, or a primitive, and it's not going to be one of those, and then it's just going to crash. So my CEK machine crashes because I try to access a field of an object that doesn't even have that field. But these are both, though, getting stuck is, it's not, it's inelegant. And crashing is also lame as well. So we want to add the idea to explain what errors mean inside of our language. And there are broadly 2 techniques. The basic idea is that we want to look at all of the rules where something doesn't apply and explicitly go in and define them. So here's the way that we typically do that. What we do is we add to our language. We'll call this language J9. We'll call this language J8. And J8 is going to have just one more feature. It's going to have a feature called abort E. And the rule for abort E is the following. It's going to say that when you get to an abort with a value, then you just return that value. Notice that it is not E of V. This is really the first time that we've had a rule like this. It says that if you're in a context where you get to an abort, you stop the context and just totally throw it away, and you just go right to the abort. What does this look like in the CEK machine? In the CEK machine, we would say that if you get to abort E, and there's some environment, and there's some continuation K, then what you do is you focus on that E, you leave the environment alone, but here's the thing that's really weird. You go back to kret. by going back to kret, we're throwing away what used to be happening, that's this e, and we're going to kret instead. And so what abort does is it allows you to exit a program early, meaning that you can now detect errors and have them stop. Okay? So once you do that, then what we do is we go meticulously through our language and we add all the rules that used to be undefined. So for example, we would have a rule like this that would say, if you have a value u and a value v, and you're trying to apply u as v, and u is not a lambda and not a primitive, then in that case, we're going to go to abort of something like, not a function. Not a function. Okay, and there would be another rule that would say something like, if we get to a set box of uv and u is not a pointer, then in that case, we'll go to abort of not a box, and so on. And we would meticulously go through our language and make sure that we've handled every single different possibility and turned into a certain abort. Okay, so this is hopefully fairly straightforward how we could do this. But hopefully you are familiar with programming languages that have some other way of dealing with circumstances like this when there's an error, namely the ability to what's called a throw catch, where what throw catch means is that we can generate an error and then potentially capture it and do something different. So let's implement that feature next. So this is going to be our J9 language. And our J9 is going to be E, but we're going to extend it with two new things. With throw E, which is going to generate an error, and try E with catch E. Now here's an idea about how it works. If you wrote try +1 throw 2 with catch. Actually, I don't like writing with. Let's change that to just catch. Try E, catch E. Catch. Now catch is going to expect to get a lambda. And that lambda is going to take as an argument the exception value. So here we'll write x minus 1. Okay? So this program is going to evaluate to 1. And the reason why is that we try to evaluate this, we see the throw, and then because there's a throw, we then turn it into -2, 1, which then is, of course, 1. Okay? So what throw does is it finds the nearest catch, and then it calls the appropriate function. Here's how it works. We update our evaluation contexts to have a new case that says try E, catch big E. We're going to evaluate the catch block first. Then it's going to say try big E, catch V. Okay, so we're going to evaluate the try block after. And then here are the rules. One rule says E of try V, catch U is going to go to EV. The idea here is that if we reduce that to a value, then that means that we throw away the catch because we don't need it. Now the next thing is more interesting. It says that what if we're evaluating a try and we get to a throw? And then we have our catch, U. Well, in that case, what we want to do is we want to turn this into e of u applied to v. We're going to call that u function with v. But now there's a little bit of a trick, which is that we want to find the nearest throw. So for instance, in this case, that throw wants to find that one. So the way that we do this is we use an additional kind of context that we're going to call L. And what L is, it is a throwless context. Sorry, a try-less context. So L is going to be what E used to be. So whatever it used to be for J8. But it's going to have only one more rule, and that one more rule is just try E, catch E. In other words, it doesn't have that rule, not this rule. What this means is that this L right here is a piece of code that does not have a try in it anywhere. Meaning that this catch right here is the closest one. All right? Whew. So, how can we, oh yes, and then one more thing, there's one more rule that we need, which says that what if we are in a catchless context and there's a throw? Well, in that case, we just turn it into an abort. And then, of course, the program exits with this value. All right. Now, how can we implement this in the CEK machine? We're going to call this CEK 5. And CEK 5 is going to have abort, try and catch, and throw. And here's what we're going to do. We're going to update our K component so it has two new kinds of continuations. One is going to be called a pre-try K, and it's going to have an E and an environment and a K. And then it's also going to have a try K, and it's going to have a value and a K. All right, and here are the rules. When we get to a try of EB and a catch of EC with some environment and some K, then we're going to turn that into focusing on the catch, because we have to evaluate what that is. We're going to leave the environment alone, and we're going to have a pre-try continuation that has the body of the try, the saved environment, and the old continuation. Okay, eventually, that catch handler is going to be evaluated. So we'll call that VH. There's going to be an environment that we don't care about. There's going to be a pre-try K with the body, an environment, and a continuation. We're going to focus on the body, restore the environment, and then we're going to put in a try continuation that has the handler. So now that handler is saved so that we can look at it later. Now imagine that we're evaluating and we get to the answer and there's a try continuation there. Well, in that case, there was no throw, so we don't care about it. So we just remove it. And so since we remove it, that means that we're going to return the answer, the empty environment, and the old continuation K. So that's the good case. However, what if we get an exception? If we get an exception, that means that we get a throw of an E with some environment and then a try K of the handler VHK. So what do we do there? What we're going to do in this situation is we are going to focus on the E, that's the exception value, leave the environment alone, and here's the cool thing. We're going to construct a new application. This new application is going to call the handler. It's going to have no environment because it's going to have no other arguments. and then it's going to restore the k. So what this is going to do is it's going to make it so that if there's a throw, we just turn throw into a function call on that handler. But now, what if there were a throw that wasn't right adjacent to a pre-k? Sorry, for a k. So for instance, what if there was a throw where it had a pre-k, a pre-try k, with some environment, some expression, some environment, and some k. What we would do there is we would just pop off that stack frame and just leave the throw e alone, same environment, and pop off that k. Similarly, if we got to a throw where there was a k if with the environment, the true branch, the false branch, and the k, then we're just going to skip over those and pop them off and just get to the k underneath. Similarly, if we see a throw and we were in the middle of evaluating a function call, that means that there would be a k app with some number of values, an environment, some expressions, and then a k, and we would also just throw those away. The idea is that we are searching through the stack, popping off one stack frame at a time until we get to a try k. Eventually, however, we may get to a k-ret. And if we get to a k-ret, then that means that there was never any catch handler installed. In that case, we're going to just focus on the e, leave the environment alone, and leave the k-ret there. Because this means that we popped all the way back to the top of the stack, and we didn't need any of those continuations because there was no catch. So that means that this value throw will just go all the way to the back. All right, isn't that beautiful? Now, once we've implemented this, one thing that we can do I'll just look at something real fast. Yeah, actually, yeah, let's hold off on doing that. Okay. So what we've now done is we've extended our language to support unconditional aborts, so like abort. We've added the try, throw, catch feature, and we've implemented it inside our CEK machine. Good job. Okay, so I think that's all we need to do. So we'll be back next time with the next language feature.